But today, I'm very excited to introduce Madeline Gotkowitz, who is, and I can pronounce her name properly every other time, I don't know why. Gotkowitz, who is our brand new research director. Is that the right title?
It's close.
Director of Research.
Yes.
Montana Bureau of Mines and Geology. Division Chief. What that's like. Who's coming to us from the Wisconsin Geologic Survey, where she worked for 19 years. They did not want to give her up, but we pried her out of their sticky hands, and she's been here since June-ish, and will be here until the end of time, because we're not going to let her go. While she was working as a hydrologist at the survey, Wisconsin Survey, she got her PhD in hydrogeology. She was studying the subsurface transport of human enteric viruses, and how interesting is that? Before that, master's degree at New Mexico Tech in hydrology and a bachelor's degree from Smith College. But she's from California. She was born in San Diego, apparently to the wrong parents, because she said she wasn't really supposed to be Californian. She said she's meant to be a Montana, I think. So, take it away, Madeline.
Well, thank you, Colleen. It's clearly I'm still in the honeymoon period here at my new job with that introduction. If I'm encouraged to stay for that long, we'll see if that indeed holds. But I'd like to thank everybody for a warm welcome to both Tech and to Butte. I've really enjoyed the past couple months. I am a very proud graduate of New Mexico Tech, and I am just so pleased to be back at a college campus that's this state mining campus. So with that, I will take this opportunity to speak a bit about a method, a technique that's very near and dear to my heart, the use of borehole geophysics and visualization techniques to understand the subsurface. I wanted to start, to start with just a couple of shots to photographs to alert you to some of the similarities between the groundwater issues in the upper Midwest and here in Montana. One of the things that we were primarily concerned about at the Wisconsin Geological Survey was the quality of groundwater that was available for public water supplies and the thousands of very small water supply systems that dot the countryside in Wisconsin that serve very small villages and towns, yet still have to meet the set of federal standards for drinking water quality. Similarly, we were oftentimes working with counties where there were a lot of new subdivisions coming up in traditionally rural areas. So we would find situations where we had very beautiful new homes built within just a couple hundred feet of their neighbors' septic systems. And given again that many of these homes are built on private water supplies, we concerned ourselves quite a bit with the quality of water at private residential wells in addition to public supply wells. In Wisconsin, as you may know, we have a lot of cows on the landscape and in barns. And of course, where they are confined in kind of extremely large dairy operations, there's a concentrated generation of manure that's then applied to the landscape around those farms. In many locations in Wisconsin, we're dealing with fractured dolomite. And these next shots show a stream flowing down into a fracture at the surface in that dolomite. This lower shot is the picture of somebody's boot, and that water flowing from the stream and the field into the subsurface, so directly into the groundwater system, where we've got private drinking water wells within very short distances of these types of karst features in the landscape. So I think some of the issues that were addressed or at least we improved our understanding of in Wisconsin through borehole geophysics have some similarities here in in Montana, even though the rocks are quite different. Just to start with some basics, I put up a series of photographs of core. This is of a very prolific sandstone aquifer in Wisconsin, the Wanawak sandstone. This is an aquifer. The scale just of inches on this photograph. We think a lot in the hydrogeologic world about aquitards, that is formations that are less permeable, that are more resistant to both water flow and the transport of contaminants. But we're also very concerned with identifying the contacts between aquifers or sandy intervals and dense materials, shales and clays that form these aquitards. So one thing that I need to do to help me understand flow in the subsurface and help me understand the water quality and the water quantity issues that affect these systems is to understand the depth of these contacts, the thickness of the aquitards and the aquifers, and then their lateral extent. Our colleagues at the Minnesota Geological Survey coined the term aquitardifer. So we think of an aquitardifer as a geologic unit that's very heterogeneous. You can see here in the Tunnel City sandstone, there's some sandy intervals in this piece of core, and there's some drapes of both clay and glauconitic rich clay here that you can see in green. So this formation is a bit of a tricky one to understand in the hydrogeologic context because laterally it's very productive. There's a lot of flow in the lateral direction because these sandstone units are fairly continuous within the Tunnel City, but vertically it's fairly resistant to flow and transport because of this continuous succession of clay drapes. So without the benefit of core, it would be very difficult for me to understand the scale of this heterogeneity in the subsurface. Core, as you know, is really expensive to collect. And so that's where I'm looking for other types of tools to help me understand both the heterogeneity and the anisotropy in the subsurface. Another issue that's very important in thinking about contaminant transport in, if I can move that mouse, in groundwater systems is the prevalence of fractures. So here's a picture of dolomite in a quarry outcrop. We can see that up close these bedding plane fractures are laterally continuous. In fact, they extend across the quarry floor. There's also, in this particular quarry down in the right, there are some vertical fractures that kind of make you wonder why these guys are standing right there, but nevertheless, they through-go a good portion of the rock, and we can see them up in this quarry as well, through-going vertical fractures. That we also have fractures in our igneous rock in Wisconsin. The fracture patterns are quite different, of course, because they're generated by different geologic processes. These might have been tectonically induced at some point in time, whereas I think a lot of the fractures in the sedimentary rock, again, are along these bedding plane contacts where there's been some change in the deposition of the sandstone or the dolomite. So how do I think about those fractures in the subsurface? I want to be thinking about whether or not those fractures extend back from those quarry outcrops. So let me back up for a minute. You can imagine, if you aren't as familiar with geology as those of us who've spent years thinking about it, you might go up to the quarry wall and you would say, well, sure, the rock is fractured here, but we don't know that that's what it looks like behind that hill. We think that rock is fractured there because we've blasted in the quarry, we've carted rock away, and so most of this is the result of weathering or exposure. So part of my job as an employee of a state geological survey is to convince the public that I know what I'm talking about when I say, well, maybe that's the case, but with some of these fractures, in particular the bedding plane fractures, because we can see evidence for them all across the quarry, we're convinced that they're laterally extensive. The vertical fractures are more challenging in some cases to make an argument for to the layperson, and even to myself, of course, because I'm quite uncertain how much of this is due to blasting in the quarry. And so that's where I want to go back to core and look for fractures that might have a little bit of wear around them. There's a little bit, it's hard to see in this image, but this fracture wasn't straight at the edge, and so I entertained the thought that this fracture might have been in the core before we brought it up to the land surface. So there may have been extensive fracture in this shale while it was still undisturbed. Here's another example where I would have a harder time making an interpretation of this fracture and whether or not it was present in the subsurface or it was due to kind of the release of pressure, if you will, when we brought it up to the surface. So I'm going to be looking for tools that help me understand the location of fractures in the subsurface, their prevalence in different formations around the state, and I'm also going to be looking for tools that help me identify when a specific fracture is active, when water is transmitted along it, and fractures that are not hydraulically active in individual wells. And so I'll talk quite a bit about that in the upcoming slides. I wanted to provide you with my, I guess it's kind of my laundry list of why I am so enamored of borehole geophysics. So if you will bear with me, I will read to you all of the types of information that we've been able to glean from these records over a decade or two of learning how to use them and apply them. From borehole geophysics, we can get quantitative measures of subsurface geologic materials and fluids. We can make use of existing wells and core holes to access the subsurface. So where core is too expensive to collect, where outcrops are very few and far between, if we can get the pumps out of wells, those are often wells of opportunity to collect more information. We can use the information that we collect with borehole geophysics to correlate both lithologic units and hydrogeologic units across great distances. So I will make the argument here this afternoon that we can use these logs to correlate Aquitards across miles of parts of Wisconsin. The lithologic logs and the hydrogeologic units that we can infer from the borehole geophysics can help us map the surface, the lateral extent, and the thickness of aquifers and Aquitards. The logs can supplement geologic logs and drillers' logs in a way that, in some ways, because it's quantitative, is fairly objective, and it's also very detailed if we can take the time and collect a high-quality data set. Of course, oil and gas industry has used borehole geophysics for decades, and it's been used widely in the water industry as well. But I was new to it when I started working at the survey, and about 10 years ago we were able to secure some grant funding to kind of bolster the quality of the equipment that we had, and that really led to my understanding the power of the method. And I've got a couple slides in here from our bureau staff in the Billings office. Jay Gunderson is an oil and gas geologist, and he's been able to mine some of the historic records at the Oil and Gas Board here in Montana, starting to look at some of the value that might be in these geophysical records. So finally, borehole geophysics and the related visualization tools can help to identify heterogeneity, anisotropy, hydraulically active fractures. It can also give us insights into the direction of vertical flow in groundwater systems. So I'll talk a bit about the direction of flow in boreholes under both ambient and pumping conditions. And finally, the tools are expensive, but of course that information is priceless. So if we can kind of get over the hump of the initial investment in these types of tools, I think that they can really lend a lot to a hydrogeologic program. In fact, the Bureau, it turns out, has a logging truck and a gamma tool that's over in the Billings office. And so I think there's a lot of potential to make use of these tools here in Montana. So to start out with, data collection, how does that work? Well, we've got a tripod that we set up either in a pump house with the pump removed from the well, or out in the field where we've got a well simply sitting out ready to have that pump house or facility built around it. We've got a data processor that's attached to a winch, and we use the winch to lower wireline cable with a tool attached to the bottom of it. The tools are all very small diameter, they're waterproof, and we troll those up and down in a borehole, and again rely on this cable to bring the electronic signals up for processing in the brains of the unit. Then we have a laptop in the logging van as well, so that we can record those data immediately. And finally, what do we get out of the process signals? We will get a series of measurements versus depth below the ground surface. So what does it look like? What do we need to have happen to access these wells? This was kind of eye-opening to me when I had the opportunity to start working with a water utility and to see what the inside of a pump house looked like. Of course, there's enormous pumps. The wells themselves make you really worry about baby Jessica or Madeline, the hydrogeologist, taking a false step around them. These are very large diameter, 2 to 3 feet in diameter wells, and we didn't have the best health and safety operation around there. But nevertheless, we lower the tools on a scale. The scale helps us understand when we've got those tools hung up in the borehole. So if we use a caliper tool, and I'll show you a picture of that, and we are running it up and down in a fractured environment or where there's a lot of dissolution in a dolomite, it's very easy to get one arm of that caliper stuck in a fracture. And the only way that we can save ourselves from having to call for help is to keep our eye on that scale and realize when the tension on the wire line has just gotten too high. This is a picture of the bowels that are hung below the pump, the bowls. So this pump and all the casing that it is hung on and that the water comes up through have to be pulled out of these wells. Sometimes the pumps are hung at well over 1,000 feet because our sandstone aquifers in the state of Wisconsin extend to over 2,000 feet below ground surface. So to get, typically we have access to these types of wells when the water utilities are doing routine maintenance on their wells or when they have a specific problem. So here's some pictures of the instruments I'll be talking about. We'll start with a description of a natural gamma tool. Gamma radiation is emitted from isotopes of potassium, uranium, and thorium. And of course, there's different amounts of potassium, uranium, and thorium in various types of rock. And we can recognize that in the gamma signal as we lower the tool down through the well. One thing that's nice about measuring natural gamma radiation is we can use it in both lithified and unlithified material. So that right there should let you know this is a useful tool in glacial deposits. So it might come in pretty handy in the eastern part of the state. We can also use it in cased and uncased portions of wells. Casing certainly affects the gamma signal, it dampens it, but you can usually see that in the log and kind of account for that in your interpretation. This tool right here happens to be, although it looks a lot like the gamma tool, this is a normal resistivity tool. And you can tell with each of the spacings on this tool that it collects electrical resistivity signals at various spacings, so in between each one of these gaps on the tool. And it measures the electrical current in the rock material around the borehole. So in fact, we do need in uncased and saturated conditions to use electrical resistivity, but it really helps us kind of differentiate between the gamma signals that are emitted by clays and shales, which have elevated gamma, but they have low normal resistivity. Metamorphic and igneous rocks also typically have a higher gamma signal, but they'll have a high resistivity signal. And so the combination of these two tools can be helpful to pinpoint the types of rocks that we're logging through. So here's an example of a gamma log that's collected in, this is Dane County over here, and you'll note that the scale is about 5 miles. So these boreholes that I'm showing you over here are well over 15 miles, if not 20 miles apart. And so what are we trying to do here? What's the goal? It's to help me understand whether or not an aquitard is laterally extensive over this entire region. So there's the city of Madison here in the middle of the lakes, but there's also many outlying suburbs that each have their own water utility in their own well field, and we want to understand what that stratigraphy is. So one thing that's very nice about the gamma tool is it can pick up the potassium that's in clay-rich facies, and you can see that we've got a pretty consistent signature here in the gamma profile, and we can link that up to help us identify the depth and the thickness of that shale facies across a regional area. So I want to show you a couple more interpretations from this area based on these gamma logs that have been used for different purposes. So this is kind of, if you will, a straight ahead use at a regional scale, just to try to make a cross section, if you will, of a specific hydrogeologically significant facies. So this is a gamma log of the Tunnel City group higher up in the stratigraphy. In fact, the Tunnel City formation is the Aquitard that I showed you a picture of early on. So it's got a lot of clay drapes intermingling with the sandstone units, and in fact it's got a relatively high gamma signal in some parts of it. So here's the Tunnel City picked out here. We're looking at about probably 30 meters of it in total. Gamma is measured in counts per second. Mostly these are on the same scale. This one on the right goes up to 150 counts. And so one thing I want to point out here is that these logs consistently show a higher gamma signal in the upper portion of the Tunnel City group and a lower gamma signal in the lower portion of what we call the Tunnel City group. And so again, this helps us understand the heterogeneity within the Tunnel City with depth across these big regional areas. In fact, these ones go over 20 kilometers, so again, quite a few miles in extent. I put up this slide, which is a much different vertical scale. So here we're really talking about only several meters in depth, and these gamma logs have been used here. I'll show you one here. This is actually collected from an outcrop using a handheld spectral gamma tool. These other two signals are gamma logs from boreholes and wells, and again we're looking at the shale facies that I started with, but we've moved out in other regions of the state to try to understand the depositional environment of the Eau Claire shale. So here we can see where a geologist has been able to interpret different depositional cycles by correlating along the gamma logs. And so this to me was a real eye-opener that we could help understand the hydrogeology in terms of the depositional environment across the state, understand how the Eau Claire shale changes from southern Wisconsin to central and northwestern Wisconsin by helping our colleagues in the sedimentary geology field do their interpretations of depositional environment. So let's talk more about some other borehole instruments. This is a picture of a fluid temperature and conductivity probe down here at the very base of this caliper. So with the fluid temperature and conductivity probe, we're able to measure properties of the fluid. We can identify changes in water quality with depth. If we see higher conductivity water, we know that it's essentially saltier. In some conditions, we can use those logs to identify hydraulically active fractures, and I'll show you some examples of that. But this tool, again, requires an uncased well. The caliper is the other part of this particular instrument. These are 3 legs, and you can electronically control those legs from the surface. So we lower the tool all the way to the bottom of the hole. Then we send the signal for these 3 legs to open or expand until they come into contact with the edge of the borehole. Then we know that tool is open, and we start to pull it slowly up the borehole, and it expands where there is a solution opening in the borehole. Sometimes you can recognize smaller fractures. Again, it requires an uncased well. There's my first typo. It requires an uncased well But we have a lot of flexibility with this tool. We can use caliper arms of different dimension, so we can use it in a wide variety of diameters of wells. I wanted to just mention some of the borehole visualization tools before I'll be showing you some of those results. Many of you might be familiar with borehole cameras. These are simply waterproof video cameras that are routinely used in the drilling industry. We can help just basically see problems with the casing, features in the borehole walls if we've got a camera where you can rotate that head. Again, we need uncased wells, and we also need clear water to be able to use a video camera. A digital optical imaging tool is a much higher resolution. It's a digital camera, and because it's pretty high tech with accelerometers and a gyroscope on it, we can orient it to dip and direction. So this can give you a pretty big advantage if you can use the tool to essentially make yourself a virtual core. Then you can identify the dip and direction of any fractures that you see in that borehole. Again, we need an uncased well, and we do a lot better with this tool if we can use it in clear water. There's a related tool, a digital acoustic imaging tool. I won't show you results from that, but this is a tool that essentially uses an acoustic signal to develop an image of the borehole wall by collecting waveform data or just waiting for that acoustic signal to bounce back to the processor. It also results in a high-resolution oriented image. And one of the big advantages of the acoustic imager is that it works really well in turbid water or in some type of drilling fluid. It can deal with those conditions. So here's an image from the optical borehole imaging tool. This is, if you will, an unrolled image on the left. And we're dealing here with just a couple of feet. So this is an image that goes from 90 feet at the top down to about 99 feet here. And with the processing software, you can wrap that image so we can see the dip and direction of this infill, likely some type of a fracture infill. So in the absence of core, this is a pretty powerful tool. This is another example on the right. I know it's a little bit blurry. It's very zoomed in. But what it allows us to do is to see that in this portion of the well, there is indeed a fracture that cuts across in place in this borehole. And again, we can get the angle and the dip of that, the direction and the dip of that fracture. So I'm going to jump ahead here to another group of tools, borehole flow meters. I'm sure these aren't geophysical in any way, shape, or form, but they are run with the same equipment, and I kind of lump them into the different tools that are at our disposal. Excuse me. So there's three types of flow meters. They all measure vertical velocity in a well. You can use them all under ambient or pumping conditions, but you need to match them to the specific conditions in a well, that is the diameter and the anticipated flow rate. So the spinner flow meter has a propeller at the end of it. So this is the picture of the propeller. We lower it on this tool, and it's got this cage around it to protect it from banging against the borehole. It's very effective at moderate to high flow rates. By that I mean that the water moving in the well is moving at least as fast as 3 feet per minute in either direction. And if you calculate that, if you back out that velocity with the diameter of a 6-inch well, that's about 4.5 gallons a minute of flow in a well, up to about 2,000 gallons per minute that you can measure with this tool. So we troll at a rate of 10 feet per minute, which means that you're sitting out there for a couple hours if you're working in a 2,000 foot deep well. If we want to get the direction of flow in that borehole in addition to the magnitude of the flow, so the magnitude again is this rate of feet per minute, or you convert it to gallons per minute. But if we want to know if that flow direction is up or down, we've got to troll both directions in the well or troll at different speeds so we can do the math to calculate which way that spinner is moving. And in addition, if you had a caliper log for the well, and you were really interested in understanding very detailed information about the hole, you could correct the flow meter data for the actual diameter of the hole if it wasn't its nominal diameter all the way down. So how does the spinner work? It's got digital fiber optic cables in it. They transmit light from the tool through these. The wires are threaded through these holes in the propeller. The instrument records the light pulses and counts per second, and then we use that to calculate a flow speed. Again, that's the magnitude and not the direction of the flow. So what do you have to do to keep the tool working? You have to make sure you don't get a grain of sand stuck in the propeller, and you've got to keep those optics relatively clean. The heat pulse flow meter is kind of a, it took me a while to get my head around this and what it's doing. This is a flow meter that's very sensitive to low flow rates, and it will get completely swamped out in higher flow rates. So how does it work? It's got a thermistor down here in this screen. It's got a thermistor up here in this screen, and it sends out, when you hit the trigger up at the land surface, you're sending a pulse of power here to heat up water. So you can imagine if the flow in the hole, so imagine this tool is used in a stationary fashion. So we lower it to a depth of interest, we set off the charge of heat, and then if we measure that heat down here faster than we measure the heat up here, we know that the flow is going downward at a certain rate of speed. So if you get a good signal, it looks like this. You see the peak of heat arriving, and you can pick an individual peak in the processing software, and you can become confident that you've got a decent measurement. A lot of times, if the signal is washed out, you know either that there's no flow or your flow is overwhelming the instrument. So there's a bit of an art to using this tool. You can put in a variety of spacers here. So what's the role of this flange is to prevent heat from going outside and around the instrument, outside of the borehole. You want to force the heat to go up through the instrument or down through the instrument, but not, for example, you don't want to see that heat go out here and then come back up in the hole. So that's why we keep that flapper or the centralizer around the center part of the tool. So here's another picture of that just kind of gives you an idea of in what setting could this possibly be useful. So here's a diagram of a core hole. There's the centralizer that keeps the tool centralized in the hole. Down here is our flow diverter. That's this flapper on the tool. This is the centralizer. Let's imagine that we've got a system where in a fractured rock system, so there's not a lot of porous media flow, but we've got a fracture at depth. We've got a fracture that's higher up in the well. And let's say we're in a general groundwater discharge area, and we've got gradients going upward through the system. Then this fracture would have higher head than this fracture, and when you set off a heat charge here, that flow would be going up through the well, and the heat would arrive at this thermistor faster. So that's the operating principle, and in fact, that's the best case to use this tool in. So here's an example of how that tool was used. This one again comes from the Minnesota Geological Survey and the USGS. So here's a whole suite of logs that they've collected. Here's the stratigraphy in the hole. They are in their Shakopee Formation. Their gamma signal helps them understand. Again, this is a reasonable scale of 100 counts per second. So we know that there is some higher uranium, thorium, or potassium elements in this part of the hole. They've got a caliper log that's identified a fracture right here, another one here and here. And they're trying to figure out if those fractures are hydraulically active. They've got a heat pulse flow meter, and they're going to run that under two conditions. They're going to run it under a condition of static flow and a condition of pumped flow. I believe the pumped flow is in the white dots. So the first thing to notice is that the dots don't line up, right? So that means that they're getting flow, a difference in the borehole between static and pumping conditions. Of course, that makes sense, but if you track these lines, let me just take a look here. If you track the lines of white dots, which are the ones collected under pumping conditions, down here they're right at about the 0 line. So they've got a pump at the top of the well, they've lowered their heat pulse flow meter to the bottom of the well, and they're continually moving it up in the well. They get no flow all the way through here. They start to see a little contribution of flow into coming up the borehole here, right? There's got to be some flow into the well because they're taking water out of it. So everything's just working on a mass balance principle. And that's how you check your work and make sure the tool's operating correctly. So here they start to see flow coming into the well. And right here, they see a kick in production, and then it drops off again. So they're going to interpret this as some type of transmissive zone here, a less transmissive zone where they may actually be losing some water into the borehole. And finally, here's their check where they know they need to be measuring about 8 gallons a minute out of that hole because that's their pumping rate. So that's the idea behind that log. So now I want to talk for a minute about spontaneous potential or self-potential logs. Again, this slide was provided to me by Jay Gunderson in our Billings office. Jay's been doing, there's my second typo. Jay's been doing a lot of work to make use of some of these old logs in the Oil and Gas Bureau's records. And he, of course, realized that measurements of electric potential, even though they typically are responding to the permeability of the unit. So here's some of his work where he can identify where he would expect the self-potential to be if he was in sand. And this red line is where he would expect that self-potential measurement to be if he was in a shale. And so these peaks identify areas where he's logging through shale. Jay has also realized that he could use his measurements of resistivity, both of the formation temperature, the resistivity of the drilling mud, and the temperature. I believe here we're talking again about the formation and the measurement of the deflection in this curve to back calculate a salinity of the formation and the mud. And so these are just an example of Jay's work to take 3 logs and calculate out depths of water fluid in the formation where he can calculate out the salinity of that formation water. And so I can see right away where as I'm sure many of you can, that this could have some great applications in the state if you're interested in taking an oil and gas well and trying to figure out if you can convert it to a useful potable water supply. So here's just another example. I'm going to, I guess I'll spend just a minute on this flow meter again to make the case to you that once these records are processed, and this one's been processed into a flow rate, just to walk you through one of these flow meter images, and then I'll just show you a couple of quick case studies. So here, where we've collected both the image, and that image again, right down here, that shows us where a shale formation is. So that's going to be our Aquitard. We also see it in the gamma log. We've got a sandstone on top of that, a sandstone below it. And we've used our caliper log here, which is just shown as this gray, to identify some significant fractures that also show up in that borehole image. So one thing that's nice about collecting all these records is we really have a couple different sets of information to help us make these inferences in the whole. So this is the 0 line on the calculated flow rate from the spinner flow meter. To the right is upward flow in the well. To the left, I believe, is downward flow, a negative value. We know that we're in non-pumping conditions because we're back to 0 flow here in the upper part of the hole. So that tells me we aren't taking water out of the hole. So again, you've got to get your head around this idea that in the subsurface, Due to heterogeneity in the permeability of all these geologic layers, we develop hydraulic gradients. And so therefore, if you've got an open borehole that crosses these formations, you're seeing the expression of those changes in pressure due to ambient flow in the borehole. So when we go down the borehole, we're seeing some inflow, downward flow here. Then we see the water is essentially lost to a fracture up here, and we go back to a condition of very little inflow in the well. We've got some inflow to the well right here because we see an uptick in the flow log, and then we see a gradual decrease in this flow volume as we go through the sandstone, and that says to me that that's generally porous media flow in here. Then we see a discrete jump in the flow log, suggesting that there's a lot of water going out of that fracture, and again an area of a thickness of generally consistent flow, and then some changes again down here as we cross the Aquitard and start losing water, gaining water from the formation as the flow log moves to the right on the graph. So here's a couple images where we can see particulate matter in the video log in the well, and that again suggests to us that we're going to see ambient flow in the hole just based on the video log. And here's a couple enlargements of the image and the caliper log to try to line up those two records. So let me just take you really quickly through a couple case studies where we've been able to claim some success using these methods to answer very site-specific questions. We've got this trout stream that of course is a highly valued resource in the community. And we can see here, under these conditions, we've got a reasonable amount of flow in that stream. When a high-capacity well in a quarry about 3/10 of a mile away from that stream starts pumping, there's dry stretches of the stream, and we've got some dead fish in the stream bed. So of course that calls for a little bit of a response and hopefully some way to bring some understanding to the relationship between the well and the stream. This is the log we collected in the well. Here's the gamma log showing that we've got a high gamma response up here, again in what we think is that Tunnel City sandy glauconitic formation. Then we go into a clean sandstone down here. We've got in this caliper log, we've noticed that we've got a fracture right here at about 110 feet or so, and some other fractures down the hole. Then we've got the flow log. Again, we calculated this, we collected that spinner flow meter at 2 different speeds, allowing us to calculate a direction of flow. And the way that I interpret this is that at this fracture, we have a lot of water coming into the well and then going down the borehole at a pretty steady flow rate and then flowing out into the sandstone. So what does that look like when it's interpreted? Again, there's a fracture, flow into the well, and flow out of the well down here. So again, we're losing water from the dolomite into the well. So how does that make sense, and what do we do with that? How can we use that to check our conceptual model of the geology and the flow system and come to some solution? Here's the schematic. We've got the trout stream that's fed primarily by a fracture in the dolomite at about 106 feet. And so knowing the depth of that fracture and being able to understand it relative to the elevation of the stream is clearly pretty important in making the argument that there's a direct connection. So flow comes from the shallow system. It enters the well. When that well is turned on, we decrease the head in the well, drawing a huge volume of water into the deeper system. And the flow goes out through the deeper sandstone in the Tunnel City that has some shale, and primarily goes out through the very productive sandstone at the base. This slide also illustrates the solution. So the original casing and grout that allowed the problem to develop, the well was cased into the bedrock formation, the legal amount in Wisconsin, which is about 80 feet. but that allowed water to enter the fracture under conditions of low head in the well and flow out. So the simple solution to the problem is to deepen the casing, grout along the side of it, and force the well and the quarry to produce water from the sandstone. So we're just basically restoring the isolation provided by this section of the geology to keep the shallow system isolated from the deeper system. So that's a really nice kind of success story for a site-specific example. We were able to identify a hydraulically active fracture. We measured about 100 GPM going from that fracture down into the well. And the solution that was suggested, extending the well casing past that fracture, in a beautiful synergy that rarely happens in public life, made everybody happy. So that was indeed a success story. I just want to run quickly through another one. This is in the city of Madison, where we had a big production well located close to Lake Mendota. That well is about 715 feet deep, and it produces a lot of water, 2,500 gallons per minute. It has a very high static level. That means it's relatively inexpensive for the city to pump water out of this well, and they run it nearly continuously year-round. However, the chloride concentrations in this well are approaching the secondary MCL, the secondary, so that's a guideline for aesthetic issues, in this case, taste. There is a spring right nearby that feeds the lake. It's called Merrill Springs, and in 1910, before that well was constructed in 1960, that spring house next to the lake was a gathering place, and it was a really nice park. When the well was installed, the spring dried up, and then in 2008, when the neighbors complained enough to the water utility installed a shallow well next to the spring box and pumped groundwater into the spring box to restore the aesthetic value in the park. Yeah, it's pretty interesting. It was an interesting solution, but of course there's also people in the neighborhood and of course at the water utility who recognize the relationship between the well and the springs. So let's get back to the initial driving problem here. This shows chloride concentrations and sodium concentrations in two of the city's municipal wells from 1993 to about 2010. They are an upward trend, and that is largely due to de-icing with sodium chloride in the city of Madison. Well 14, the one I was just talking about, is also located near a kind of a focal point of the city's stormwater drainage system. So everywhere that stormwater is collected and goes through an unlined or an old portion of the stormwater system, there's the potential for that stormwater to recharge the groundwater system, potentially near that well. So that's another concern. We don't know if the salty water is coming in generally through recent recharge or if it's focused there by the stormwater system. So here's just a quick slide of the cross-section looking at the well construction in the city. This particular well of interest by Spring Harbor is cased into the upper aquifer, but similar to the well near the trout stream, it's uncased through the lower portion of the upper aquifer across the regional Aquitard, and it's open to the deep aquifer. So that's what we're going to keep our eyes on as we go through the logging exercise. Not all the wells in the city are constructed in that way. Some of the wells are cased through the Aquitard and access only the deep sandstone aquifer for their water supply. So here's the geophysical logs that we collected under static or non-pumping conditions in that well. This diagram just shows you the depth of the casing and under non-pumping conditions, the static water level in the well itself. This is our temperature log, and so we know that as we go through the casing, the temperature is changing with depth, but then it's fairly steady, increases a little bit probably with the geothermal gradient at depth in the hole, but we have a couple of big swings in fluid conductivity in the saltiness of the water. We've got our caliper log that highlights the depths of a few fractures, and we've got our gamma and resistivity logs. This in particular helps us identify the depth of the Aquitard. So now we're going to run that same suite of wells, but we're going to have lowered a pump after we lowered our tools in the hole, and we're going to pump at a pretty high flow rate of over 1,500 gallons per minute, and then we're going to rerun this suite of logs. So we saw that over here in red, this fracture, again at about 110 feet or so, and this fracture line up pretty nicely with swings in the conductivity log shown here in red. So here we're going through the casing. Here we've got a big kick in conductivity, and it holds steady through here. Then the water quality gets a little bit better, that is less salty, as we go down through, and there's another kick right here. Similarly, in the flow log, and I believe this is unprocessed, so I believe this is just red in terms of feet per minute, we see a big kick in the flow rate while we're pumping at this fracture, closely aligned to this fracture, or closely aligned to the base of the casing. We still get some productivity in the well. Water's coming into the well in here. Water's going out of the well a little bit in this section. But if we skip now to the bottom of the hole and read the log from the bottom up, at 1,550 gallons per minute, there is no flow from the deep aquifer, from below the Aquitard. All of this water demand is met by the transmissivity of the upper system. It's met by quite a lot of volume from this fracture, and again, quite a lot of volume from this fracture. And so what does that leave us to tell and work with the water utility on what they might do? We think that about 80% of the produced water at that pumping rate comes from fractures primarily at depths of 117 and 230 feet. We also did some discrete interval sampling with our set of tools where we've got a piston sampler that we can lower to a specific depth. From that sampling and from the fluid conductivity log, we know that we see the highest chloride associated with the shallowest fracture. We also found out that the bottom part of that hole, again, when you're pumping at the flow rate we used, the bottom part of the hole contributes very little flow to the well because most of the demand for water is met by the upper section of the well. So extending the casing to 250 feet might improve the water quality. In fact, if it's properly grouted, it very likely will improve the water quality. It might increase the natural discharge to those springs that are of interest to the neighbors in that area. But we also know that it may reduce the capacity of the well. So if the casing is extended through the most transmissive part of the groundwater system, of course the water utility isn't going to have that, likely won't have that same capacity from that well if they're just drawing from the lower conductivity, deeper sandstone. So I wanted to talk about both those examples because they both give a lot of insight into the hydrogeology at specific sites, but they really don't always point to a simple solution that will keep all the stakeholders at the table. So finally, again, just to wrap up, why do I get so animated when I think about borehole geophysics? Because it's really such a big help with hydrogeologic mapping. It's a great diagnostic tool if we're interested in fracture contribution to flow or to contaminant transport. It's relatively inexpensive if you've got existing wells and borings that are uncased, or in some cases for the gamma logs, even if you've got cased wells and borings. It may not be as useful in areas where bedrock wells are fully cased, and I know that might be the state over large parts of Montana. And again, Jay's demonstrated that it might be useful in identifying freshwater lenses in some of the deep wells completed across Montana. So with that, I also just wanted to put in a plug for geophysical logging in cold winter conditions, which sometimes is successful when the computer doesn't freeze up. So with that, I'd be happy to take any questions you might have.